Hi everyone, so we'll continue with infrared spectroscopy. This video I'm going to share with you on the factors that affect the position of absorption band on IR spectrum and also the factor that affect the intensity of the absorption band. So what you can see here is an IR spectrum. The absorption band are this. We have already learned about this in the previous video. So you can see the absorption bands, they are with different wave number. Okay, they are with different wave number on the spectrum. They are also with different intensity. Okay, the band, they are also with different intensity. Some are very intense, some are with medium intensity, some are with weak intensity or weak band. Okay, so first let's look at the factors that affect the position or the wave number. Okay, the wave number of the absorption band. So in the previous video we have seen that the principle behind this IR spectroscopy. Okay, you know that atoms and atoms, okay, atoms and atoms, they are connecting through bonds. Okay, they are connected by bond and the bond is vibrating. So the vibrating bond is actually behave or we can describe the vibration of the bond. It is like a spring. Okay, it is like a spring. So we can actually use Hooke's law. Okay, we can use Hooke's law to describe or to relate the strength of the bond and the mass of the atom with the frequency of the vibration. In Hooke's law, okay, this is Hooke's law. This is Hooke's law. So this is frequency. Okay, frequency is similar with wave number. It's also directly proportional to energy. Okay, so when I mention frequency, is actually the same with wave number. And K, okay, K is force constant. So it relates to the bond strength. Okay, it's the strength of the spring, but in a compound, of course, it is the strength of the bond. Okay, so for mu, it relates to the mass. Okay, to the mass of the bonded atoms. So by looking at the Hooke's law, we can know the relationship between the bond strength, the mass of the bonded atoms with the wave number of the absorption band. So first, let's look at K, the force constant or the bond strength. When K increase or when the bond become stronger or when you have stronger bond, the frequency or the wave number increase. Let's look at example. Let's compare different carbon-carbon bond. We have carbon-carbon single bond, double bond, and also triple bond. When you compare the bond strength of double bond, single bond, and triple bond, okay, the bond strength, the K or the bond strength, for single bond, it is lower. Double bond, you have higher bond strength, and triple bond is the strongest. Okay, so by using the Hooke's law, we know that when force constant increase or when the bond strength increase, the wave number also increase. okay, the wave number, the wave number also increase. Okay, so the relation is directly proportional. So actually, if we compare these three, the wave number for triple bond is 1250, double bond is 1650, and single bond is 1200. Okay, you can see triple bond is with higher wave number, followed by double bond, and single bond is with the lowest wave number. This is because of the difference in the bond strength. This also can be applied when you compare the wave number for oxygen, carbon-oxygen bond, or carbon-nitrogen bond. Okay, now let's look at the mass. Okay, the mu. Okay, the mu, this one. From the equation, we know that the relation is now inversely proportional. When you have high mass, okay, when the mu or the mass increase, the wave number decrease. Let's look at some example. If now we compare CH, CO, and CBr, bromine. If you compare the mass, you know that bromine is the heaviest. Okay, it is with high mass, followed by oxygen, and hydrogen is with lowest mass. Okay, hydrogen is with the lowest mass. So just now we have seen that the relationship between mass and frequency or wave number is inversely proportional. So CH bond is with higher. CH bond is with the highest wave number, followed by CO, and the carbon bromine bond is with lower wave number. So maybe I show you the number, it's easier for you to relate. Okay, so you can see carbon bromine is with lower wave number, and carbon hydrogen is with high wave number. It means that you can see the absorption band appear at the higher wave number region. So this is the relationship between force constant, the bond strength, K, okay, the bond strength, and also the mass with wave number. Now let's look at the factors. Okay, another factor, which is the hybridization of the carbon. Okay, so if now we compare different hybridization state of carbon for the same bond, okay, for example, you have all are the same, okay, they are all CH bond. But if let's say now you have different hybridization state for carbon, for example, this is sp3, this is sp2, this is sp. Okay, sp3 is the one with single bond, this is the one with double bond, this is the triple bond. Okay, but now we are focusing on CH bond. CH bond, okay, is the one that we want to compare. They are the carbons, they are now with different hybridization states. Okay, and the relationship or the effect of this is the greater the S character, the stronger the bond. Okay, the stronger the bond. So if you look at sp, sp2, and sp3, in sp the S character is 50%. Okay, in sp the S character is 50%. Okay, for sp2 the S character is around 33.3%. In sp3 is around 25%. So you can see in sp the alkyne, the one with triple bond, okay, the alkyne CH it is with greater S character. So the wave number is higher. Okay, the CH bond with the carbon with sp hybridization state is stronger. So the wave number, so now the wave number is higher. Okay, it is around 3,300. For sp2 carbon, okay, it is around 3,100. For the single bond one is 2,900. Okay, so you can see the alkyne CH, it is with higher, followed by alkene CH and alkane CH. They are with different wave number. So next, let's look at the factor that affect the intensity of the band. Okay, the intensity depends on the size of the dipole moment change associated with the vibration. So you have different bonds, different atoms. When the greater the change in dipole moment, the more intense the absorption band. Let's compare these three: OH, NH, and CH. Okay, the dipole moment, if we compare these three, CH is with a greater dipole moment, followed by NH, and CH, it is with lower dipole moment change. Okay, this is related to electronegativity difference. So the greater the dipole moment change, the more intense the bond. So it means that on the IR spectrum, OH absorption band is more intense, okay, followed by NH, and CH is less intense. Okay, the intensity of the band. Okay, the next factor is the number of the bond. So if let's say now we are looking at CH bond. CH bond in methyl iodide, okay, methyl iodide, and also the CH bond in octyl iodide. If you calculate, okay, if let's say now you draw out the structure, and you calculate the number of CH bond. In methyl iodide, you have 3 CH bond. In octyl iodide, you have 17 CH bond. So in octyl iodide, you see more intense absorption band for CH because you have greater number of CH bonds in octyl iodide. In compared to methyl iodide, it could be less intense. Okay, and another factor is concentration. This is the explanation is actually similar with the number of the bond. Okay, concentration. When you have concentrated sample versus diluted sample. In concentrated sample, you have more number of a molecule, and of course you have more number of bonds, and the intensity, of course, it will be higher compared to diluted sample, which you have low number of molecule, low number of bonds, and you have lower intensity. That's all for the factors that affect the intensity of the absorption band. Okay, we have seen that the factor and also the factors that affect the wave number of the absorption band. So the bond strength and the masses of the atom and also the hybridization state. Okay, the hybridization state of the carbon will affect the wave number of the absorption band, the dipole moment change, the number of the bond and concentration of the sample affect the intensity of the absorption band. So that's all for this topic. Thank you.